Okay, we're going to take a break from the Fourier transform for a couple weeks. We're doing another topic on information, compression, and error correction. It's not usually something that's taught in this type of a course, but it's very popular. We've been teaching it for the last quite a few years, and the students usually like it. I think it's very fun material. So like I said, it'll be kind of a different flavor than the rest of the content where we're focused on Fourier transform. Hopefully you got my message that the Friday's lecture I added to the video. So you should go back and watch. I put another half hour of lecture at the end. Okay. Great. So I said this material is very fun, and it is. The real fun is going to begin next time, although hopefully you'll find what we do today fun as well. Today I'm going to try to connect together sort of what we've been talking about and give you some background that will be useful for getting into the content of information next time. Okay. So consider the process of going from an analog signal to a digital signal. Okay, what do we mean by an analog signal? Well, often we're talking about continuous time signals that take on real values, like something you would measure from some sensor somewhere. So I'll say continuous time, the domain and range of this signal are both, let's say, the real numbers are. Okay, and then we're going to end up with something that we're calling digital. And what we mean by that is it takes on like a finite set of values. All right, now the process of doing this, the standard process, it involves two things. We've talked about one, the lecture last time was about sampling, but I'm going to argue, well, it'll be easy to see, sampling isn't the whole picture here. Okay, we actually have sampling and quantization. Okay, so consider the following block diagram. In comes some signal. Okay, some function of time. So this will be an implementation of going to from analog to digital. All right. Okay, so first thing we want to do is apply a low-pass filter. That's to do anti-aliasing because we're going to end up sampling. So out of this low-pass filter, we get the signal that's been smoothed a bit. Get rid of the stuff we're not going to be able to keep because of our sample rate. All right. Now we're going to have something that I'll call sample and hold. This is just going to kind of explain how, the mechanics of how you would do a sampler. You have something that basically outputs the signal sampled, and each sample is just held out, so it's over the sample interval. Something like that. Then you're going to have an analog to digital converter. And what this does is, for each of those samples, it rather than just some real valued signal came in, and the output is some bits that describe that value. Okay, and then you would do something like put this in memory or do some processing with it. I'll just say memory. Even if you're doing something in real time, which means this is the process of going from analog to digital, maybe you're going to do some sort of signal processing, and then you're going to bring it back to analog. Okay, even that is going to require some sort of memory. In that case, you might call it a buffer. So you could call this a buffer if you're doing some real-time thing where you're not just storing it indefinitely. But it's still memory. You're going to hold on to some history so you can do some processing. Now there's a Okay, so why was this low-pass filter here? That was for anti-aliasing. Okay. You actually, there's some clock that's determining the sample rate, and it's also, determining when you move to a new piece of memory to put the next value. This ADC stands for analog to digital converter. So you see the combination of all of this ends up with just a sequence of bits, so you are really a digital signal now. Okay, we've talked about some of this before. For example, suppose your signal was band limited so that this anti-aliasing filter actually didn't do anything. It wasn't needed. Then you get that to this point here, to this point right here, you actually have no loss of information. Of course, if band limited. So if the anti-aliasing filter didn't do anything, you might lose something there because you're sampling at too low of a rate. But let's assume that didn't happen. Then this sampling process, that was the whole point of the last couple of lectures, right? The sampling process doesn't lose information. Now, most classes on information signals, the first class that you would learn, you don't get into the second process of doing the analog to digital, the quantization. Okay, so you kind of just stop here, and you talk about samples. So now we're going to talk about this quantization part. Okay, so let's give an example of quantization so you know what we're talking about here. So, for example, here's 2-bit quantization. Suppose you have some signal to begin with. Okay, and we're going to first sample it at certain moments in time. So we take these samples. Let's see. Okay. Now, the quantization step, the analog to digital converter, if it's 2 bits, is going to do something like this. It's going to have, let's say, these are meant to be horizontal lines. It's going to have something like 4 different values, each assigned to a 2-bit number. All right, and then round each sample to the nearest point. All right, so let's draw that. So this is going to be, this one's going to be rounded to there. That's going to stay about where it is. Okay. You see, the output of this quantization will look something like those red points. Okay, so in other words, what would be written to memory would be something like 0, 0. I'll put commas just to mark when I'm on to the next one. 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1. And that would be what's stored. All right. Okay. So this results in some loss, obviously. So let's let x hat of n be the reconstruction. The values, those red dots that I marked, are what you get back when you read this signal out of memory, right, after the quantization. So it's the red part here. All right, we'll call that x hat. Then we can say the error in this signal is also itself a signal. It's a function of n. The error of n is the true signal minus this reconstruction. Okay, so in other words, we can draw a new signal here. This is the error of n for the above. And it's going to be something like this. This first one, so it's the difference, right? The true signal was below the reconstruction, so it's like this. Okay, and the next one is slightly below. Oh, no, sorry, it's slightly above. I went the wrong way. This way. Next one's quite a bit above. Okay, so there's an error signal, all right, representing. So if we add this error signal to our reconstruction, then we get back the true thing. But we don't know the error. We lost it, all right. Sometimes we'll call this noise, even though it's not really it's noise that we produce because of our quantization, but I'll call it noise, I'll call it error, whatever, something along those lines. Okay? Now, really I don't have a lot that I'm going to teach on quantization. What we're going to learn about information and compression is sort of a generalization of quantization, and we'll see some examples of where it's applied. But let's notice something about audio that we're familiar with, or maybe somewhat familiar with. CD audio uses a sample rate of 44.1 kilohertz. Okay. It also is often stereo, so that means it has two channels it's recording. And the quantization level, generally 16-bit is the standard quantization, although it's not too uncommon to do a higher level of quantization, so we'll say or 24. Okay. Now 16-bit quantization is how many different levels? So, we said 2-bit quantization gave us 4 levels. 16 bits going to give us 2 to the 16. So that's quite a few levels. 2 to the 16 is 65,000. So that's how many quantization points we get to round to. All right. Okay, but let's calculate then how many bits are being measured from our signal if we want to save this to memory, right? We should multiply this out. And so just multiplied all those numbers, and what we get is about 1,000,000.4 bits per second. Now let's convert that to something we're more familiar with. Let's first take it to bytes. It's 176 if we do 8 bits in a byte. This many bytes per second. And now let's convert it to minutes because we're used to listening to music. We know how many minutes those are. So that's about 10 million bytes per minute. Okay. The bottom line here is we're doing roughly 10 megabytes per minute to store CD audio. Okay. Now, do you ever look at file sizes of songs you download or you listen to on your devices? Roughly how many bytes per minute are they? About 1. Yeah, I think 1's pretty common, right? You can get them that are more depending on what compression was used, but they're basically 1/10 of this size. So the breakthrough happened in the 90s. You got MP3, which was really the big breakthrough for audio compression. I mean, now there are other things that work as well or better than MP3, but that got you that factor of 10, decreased file size, and really MP3, even with that reduction in file size, was shown that the most listeners could not tell the difference between that compressed file and the original. So you were losing information during that compression. It wasn't that you actually just figured out a better way of storing it. You lose a lot, but not anything people could hear. Okay, and that was the key to making these. Back then, it really mattered that you reduce this file size if you were going to download anything on the internet. Speeds were slower. Okay. So, and this, by the way, this calculation we did doesn't even include any sort of overhead that would be used to store this. There are standards in how the information is actually stored. This was just purely calculating how many bits came from those samples. And this isn't even the highest quality, right? We only did 16 bits here. Okay, so you're actually going to learn, in a couple of weeks, you're going to do a lab that kind of addresses MP3 compression using a lot of what you've learned using Fourier transform and some of the stuff that we'll talk about for the next couple of weeks. So now what I'm going to do is switch gears here. At the end of the lecture, we'll come back to quantization for a little bit. I want to do a probability primer that'll help us with the content we'll do for the next few lectures. Probability. Okay, so now, many of you will or have taken a probability class. And many of you, if you haven't taken it yet, are going to find that this is one of your favorite classes. It's a fascinating topic. I'm barely going to scratch the surface here. In fact, what I show you today won't really be any of the cool stuff. But let's just get some things under our belt here. So let's say X, capital X here, is a random object. Let's say with outcomes in some set. Which we'll denote by omega. Okay, so omega is a set of outcomes. Okay, so for example, I'll give you an example where X represents the outcome of a sporting event, or some event where there's a winner, whether a team wins or loses. Okay, so then in this case, omega is going to be the set win, loss, or tie. Okay, those are the possible outcomes. X is random, but it's going to take one of those values. Right? Okay, so let me give a concrete example. Suppose I know the probability that X wins is 70%, X loses is 20%, and of course then tie has to be 10%, because the first obvious thing we know about probability is that the outcomes, the probabilities all have to sum to 1. So they're non-negative, can't have negative probabilities, and sum to 1. Okay, first rule. Give you another rule that's pretty obvious. Consider the probability that either X wins or X loses. Okay? Well, we know that needs to equal the sum, 70% plus 20% equals 90%. So the other basic rule of probability is that if you take a collection of disjoint events, their probabilities sum. All right? We call this whole thing, this is an event, it's a set of outcomes. So you can talk about probabilities not just of the individual outcomes, but of sets of outcomes. All right. Say the probability that X is in this set is 90%. Okay, now we say that we have a random variable if this set of outcomes is a subset of real numbers. Okay, so now we're talking about random variables where the outcomes are numbers rather than win, loss, and so forth. Call this a random variable. There are a couple types of random variables I'd like to distinguish between: discrete and continuous. So we'll talk about discrete first. So discrete is that x takes one of finitely many possible outcomes. In fact, it doesn't have to be finitely many. It could be countably many. Countably many means it could be infinite, but it has to be a certain type of infinite that you could list in a sequence. Okay. So countably many values, just think of this as finite. That's okay for now. If you have such an x where it's taking on this set of values, then we can define the distribution. By the way, the distribution is the name of what we call this assignment of all the probabilities. Okay. So we have what's called a probability mass function. And it simply is the following. It says that we usually use p sub x. That sub x is telling us this is the probability mass function for the random variable x. Is going to be equal to the probability that x equals that particular outcome A for all A. Okay, so that's what the probability mass function is. It's just some notation for saying what's the probability that x equals any particular value. And note that if we then want to, by the rules we've already talked about, if we want to know the probability that x is in some event S, so not a particular outcome, but some set of outcomes, well, it's pretty simple. We sum over all outcomes in that set this probability mass function. Okay, so we'll just sum all the probabilities of the different things. All right, let's actually look at an example here. Okay, suppose that our probability mass function. Now, let me mention something. You'll notice it's actually more standard to use. So this variable here, A, is just a dummy variable for this function. It just appears on both sides. Okay, it's standard to use little x or whatever letter you're using for your random variable, to use that same letter here, but lowercase. So, I'll often do that. In fact, I'm going to do it here. But I chose to put A in, and I'll put A in a few times throughout this lecture to be less confusing, just in case it's your first time seeing that. Because, little x, big X might be hard to tell apart on handwriting. Okay. But the idea is, suppose this graph shows a particular probability mass function. It's got a value of a half, a quarter, a quarter. Okay. Actually, maybe it would have been better if first I had written out a formula for it. So here is precisely the definition of what this function is. It's a half when x equals 0. It's a quarter when x equals 1 or 2, and it's 0 else. Okay, so here's a probability mass function. We can verify that it all sums to 1. It's non-negative. That makes it a valid probability mass function. And what it means is this random variable takes on the value 0 with probably a half, value 1 with probably a fourth, and value 2 with probably a fourth. Okay. So we have some rules to qualify something as a probability mass function, and that is that px, the probability mass function, has to be greater than or equal to 0 for all x, and the sum over all values has to be 1. If that's true, then it's a valid probability mass function. All right. How about continuous random variables? How do they differ? Well, they don't have a probability mass function. They have what we call a probability density function. because, in fact, the probability of any particular outcome for a continuous random variable is 0. Okay, so we can't even make sense of a probability mass function. The mass is 0 everywhere. But we have densities. So here, sometimes people use an F to represent rather than a P. Sometimes they use P anyway, even though it's not a probability mass function. I'll use F just to make a distinction here. So this density function, again, I'll use lowercase x to, capital X, but subscript to represent this is the density for random variable x. And what this means is, so here's how the density should be interpreted. If you have any subset of numbers, any event, S, the probability that that event happens, in other words, the probability that x is in some set S is going to equal the integral over that set of the density. Let's compare to see why this is really the same as we had for the probability mass function. For the probability mass function, we had that you sum over the set. And now that we have continuous random variables, the sum just becomes an integral. So really, it's the same thing. What's missing is I can't write anything like this first statement. I can't say, in the probability mass function, you had a very simple definition for what value it took. It took the value equal to the probability that outcome occurred. But there's no such equivalent for continuous because the probability of any outcome is 0. Okay? So you just have to stick with this sort of understanding. The probability of being in a set is the integral over that set. Give a couple of examples here. Okay, we can do the, here's a uniform distribution. All right, we might denote this as like for uniform there, with two numbers, B and C. And that means that the density is equal to, it's equal to 1 over C minus B if the value of your random variable is between B and C. You know what, I'm going to use X just so you don't get A confused. A, B, and C are too close in the alphabet there. All right, so if X is between B and C, then it has a non-zero density. Otherwise, it's 0. Of course, you can convince yourself that there's a rule here. Let me put a rule, just like we had rules for density functions. We have a rule for we have a rule for density functions, just like mass functions. The density also should be non-negative, and instead of summing to 1, it should integrate to 1. Intuitively, this makes a lot of sense, because what is the integral? Because if we interpret this integral as a probability, we're saying, what's the probability that x is in the whole set of real numbers? That's going to be the integral over the set of real numbers of f. That probably better be 1, right? It's a real valued random variable. So that's all this rule is saying. The probability that x becomes a real number is 1. Okay. Okay, so there we have a example of a uniform distribution. Consider a special case of that. Consider uniform 0 to 2, just so I can actually look at some specifics of it. We can get a graph of this thing. It's going to be between values 0 and 2. The density has a height of 1/2, and it's 0 everywhere else. Okay, so there's the density function here. This is fx. Okay. So if we wanted to ask a question, what is the probability that this random variable is above, let's say, 3/4? All right, so what's the probability it's above 3/4? Well, that means we should be integrating on this side over here. I'm going to use another color. We should be integrating it over here. Okay, to say the probability it's above 3/4, and what's the answer going to be? What's the answer? 5/8. Okay, so we see how we can calculate probabilities based on this density. All right, here's another well-used probability density function, the Gaussian distribution. And often that's denoted with an n, script n for normal, because it's another name for the distribution. Normal, it has two parameters, just like uniform had two parameters. This distribution has two parameters. Usually they're mu and sigma squared. And the density is defined as the following. This first thing is just a constant, just to make it integrate to 1. And then here's the main part. It's e to the negative x squared, although the parameters show up here. E to the negative, it's actually x minus mu over sigma squared. Okay, so there's the normal distribution for a mu and a sigma. And really, it looks like the following. So here's x. It's centered around mu. And it's like this type of a thing, e to the negative x squared, the bell curve. And the width is proportional. This width here is proportional to sigma. Okay, so there are your two parameters, the width and the mean, where you move it to. Okay. Great. So again, let me remind you, when you have these continuous random variables, you have these densities. If I ask what's the probability that x equals 1 for this Gaussian distribution, I don't go look at where 1 is. Let's say 1 happened to be here, and look at the density. That's meaningless. The probability that x equals 1 is 0. It will not equal 1. It may equal something very close to 1, but you have to have some set that you want it to fall in if you're going to talk about what probability. Okay. Great. So now what we're actually going to use, that was sort of a background. Let's just talk about a mean, or actually an expected value. Oh, I need to give myself space there. Okay. So we have this notion of an expected value of a random variable. In fact, we have an expected value of any function of a random variable. So let g be an arbitrary function, whatever your choice of function is. G of x, where x is random. Of course, if x is random, then g of x is also random. Okay, but we have this notation that says the expected value of this function of x is defined to be the sum over all values. Okay, I'm using a sum, so let me just assume that this is discrete. Let me make a comment about that. We talked about discrete and continuous random variables. In fact, there are other types of random variables that are neither discrete or continuous. There's a third type, singularities. We're not going to even talk about them at all here. And all random variables actually are combinations of those three things. But all we care about, we're just going to care about random variables that are either discrete or continuous. If it's discrete, then the expected value is the sum of all outcomes of the probability of that outcome times the value of the function. Okay? So this would be for discrete. For continuous, we get the same thing, something very similar. It's the integral instead of the sum of the density times g of x. So, and you'll notice this that there's always an analogy between discrete and continuous. You just change the sums to integrals. Okay. Now, you might call this the mean of g of x. Because if you think about how you would calculate a mean, this is really how you do it. You look at all the times that different outcomes happened, and the probabilities are sort of telling you how often that outcome is going to happen, and you do a weighted average. Okay. So let's look at a special case. What if we just want expected value of x? That means g of x just equals x. Then, of course, this is just going to be the sum over x, the probability, times x. Okay? So this mean, so the mean of a random variable, mean of x. And sometimes this is called the first moment of the distribution. All right. Of course, if it's continuous, then you integrate. I won't always write both cases. I'll erase this because we're doing both. Okay. So let's go up and look at our examples and calculate the means of these random variables. Okay, so up here, what's the... okay, expected value of x in this case is going to equal, well, we just take the three possible outcomes here. We get, with probability a half, we get value 0. With probability a fourth, we get value 1. And with probably a fourth, we get value 2. So that equals 3/4, right? Okay. So the expected value of this discrete random variable is 3/4. How about if we go down here? Okay, let's do this one. Expected value of x. Maybe we should do, okay. Is going to be the integral of, from negative infinity to infinity, of this density. But I'm going to go ahead and say that's just equal to the integral from 0 to 2, because it's 0 everywhere else, of 1/2. And that's the density times x dx. Okay? So then that's just going to equal 1/4 x squared, evaluated 0 to 2, all right, equals 1. So the mean is 1. You could have probably eyeballed that, because looking at this density, a mean, it has a similar physics definition. It's the center of mass. Okay, center of mass of this density would be the middle, 1. Okay. Great. In general, for this up here, the expected value of x for general b and c is just going to be the midpoint, b plus c over 2. Okay, for that particular, for uniform distributions. For Gaussian, I'm not going to calculate out the mean, but the mean ends up being mu. So this picture makes sense. Okay, I'll just write it here. Expected value of x equals mu. All right. Now we the expected value has it shows up, in many settings. People often try to. That's one of the first things they'll look at of a distribution is its expected value. Let me give you one reason why expected value is meaningful. There's a law of large numbers from probability theory, and it says that if you have a sequence of independent random variables, so we'll call them x1 up to xn, and they're not only independent, they all have the same distribution. Okay, they all have the same distribution. Now, I haven't even defined what independent is. I think I will get to that, maybe later when we need it. But I think, you can just take this this theorem statement for granted, just that you have some intuition of what independent random variables should be. Then what this is saying is the sample average of that sequence. What's the sample average? That's saying 1 over n times the sum of the value of x, or in general, any function of x that you care about. Or let's say bounded function. This is going to converge to the expected value of g of x. Okay, so there's what the first, the most important fundamental meaning of what expected value is. It says if you actually take many samples and average them, you're going to approach the expected value. So it is actually a meaningful number. Okay, so let's look at some other expected values that we care about. There's a second moment, which is the expected value of x squared. All right, So it's just another expected value. I won't write out the definition. We know the expected value for any function of x. But let's see what the law of large numbers implies about this. It's kind of fun. If we plug it in, we have that this sum here of xi squared is going to converge to this second moment. But what is the left-hand side of this? Especially if we let n go to infinity. Right? That's the power of x, if x is a discrete time signal. Now it's a random signal. Okay? But if x was some randomly generated sequence and you treat that as your signal of interest, then this is exactly what we call power. So it's saying the power of this random process is actually going to be the second moment. Okay. A couple things related to this second moment. We have variance. Variance is like the second moment, but you first remove the mean. So you take x, subtract its mean before you take the second moment of the distribution. Okay. So it's going to be always less than the second moment, less than or equal. And finally, you have something called standard deviation. Which is just the square root of this variance. Square root of the above. Okay. Why square root? Well, that's just because, say x has units. Suppose x are scores on a test. Okay, you've all seen standard deviations reported to you, right? So if x is scores on a test, well, we've squared the units here. If we take a square root at the end, we're back to our original units. Okay, so standard deviation is easier to interpret because it'll be in the same units of the random variable x. Okay, so let's just go back and look at these examples again for the. All right. For the distributions I've given you. For example, we have that the variance of this random variable. Okay, we would say, well, we already have the mean, right? We calculated the mean to be 3/4. All right. So the variance, we subtract the mean. We take this formula. It's an expected value, where we take the probability, so probably 1/2 times, and for this point, the distance to the mean is 3/4. So 3/4 squared. The negative doesn't matter because we're squaring. Okay. Then we go plus 1/4 times. The distance to the mean was 1/4 squared. And the last one, 1/4 times distance to the mean was 5/4 squared. If we calculate that all out, we get 44/64. That's the variance. Okay. Let's go down to the uniform because we actually are going to use that one. So for the uniform distribution, if we want the variance here, we're going to now integrate, again, according to the probability density function, which is 1/2. But now we take the distance between x and the mean. The mean was 1. Okay, so this will be our calculation of variance. Now, this ends up being, you can do the integral, it ends up being 2/6. Okay, 1/3. So that's the variance of this particular thing. All right, I just plugged in the formula. Now, in general, for a uniform, let's look at the general statement. It's going to be c minus b squared over 12. Okay, again, I just work out an integral exactly like I had here for the general case, and you'll get a variance like that. Okay, last thing that we need to do here is go back to quantization. Say, what can we say? We can say something about quantization now. So, assume that you have some sort of your signal. Now, we don't know what it is because we're doing some sampling. We're going to treat it as if it was random. Whatever your signal is, if it's music or something like that. So it has some distribution for each sample. Okay. Now, it also usually has a so-called dynamic range. If you notice, whenever you load music into MATLAB, the values are always between -1 and 1, because that's the dynamic range of the recording devices. Okay, and they normalize it to some dynamic range. So I'm going to use that here in this example. So the signal has some distribution. I'm just going to make it arbitrary like that. Between -1 and 1, that's your distribution fx. You do some sort of quantization, which as we mentioned before, one interesting quantization is uniform quantization. And that means, it's like my example I gave at the beginning, means equally spaced quantization points. So we have this. So we have these quantization points like this, and the signal, when it gets sampled, is going to be rounded to the nearest quantization point. I've changed the axis. Before we were showing it vertically because we were showing the signal progressing in time. Now I sort of flipped it sideways. The signal x's value is horizontal here, so maybe that'll clear things up. And so basically, if the signal value is measured between here, it's going to be quantized to that blue dot, okay? And the error then will be, say it's this is the actual signal value. It gets quantized to there, and that's the error. All right, in this quantization process. Now notice if the quantization is fine enough, then no matter what the density was originally, it looks like a uniform distribution over that quantization interval. So it turns out that with fine enough quantization, the error is uniformly distributed if quantization is fine enough. And in fact, we can even say how big is that. The error is bounded based on the number of quantization points, right? It's going to be the dynamic range. Dynamic range is this, the whole width of where you did your quantization. We're assuming the signal all lived within that dynamic range. So it's going to be the dynamic range divided by 2 times the number of quantization points. Now, if we're measuring quantization in bits, the number of quantization points is 2 to the b, where b is the number of bits. So let's say it's the dynamic range over 2 times 2 to the b. Okay, b is the number of bits. So then the quantization error has a certain power. Because it's uniformly distributed, we can calculate the variance, the second moment of this quantization noise. All right, and that's just going to be, in fact, we would then treat this as a uniform distribution. For lack of time, I won't scroll up, but we would look at the variance of that uniform distribution. It's going to be exactly the following. Dynamic range over 2 to the b squared over 12. So this is the noise power. So now we can interpret quantization. Assuming it's fine enough, we can interpret quantization as an additive noise. Okay? And that noise is smaller depending on how many bits of quantization we do. So let me give you a demo to end the lecture today where I'm going to pull in a song and I'm going to do some quantization. And we'll look at the graph of it and we'll listen to it. First, I'm going to do a 1-bit quantization. This should look pretty awful. So here is the, okay. So here's the original song. And here's the quantization. It only takes 2 possible values, and it's moving back and forth so fast it looks very solid. If I zoom in, maybe it'll look more interesting a little bit. Not really. It's jumping back and forth, depending on what the original song was, but it's just hitting 2 values. Okay, so let's listen to it. So first of all, here's what song we're doing. Oh. So here's the segment of the song. That's not with quantization, right? Now here is with 1-bit quantization. Pretty remarkable that you can actually hear the song in there. Okay, now let's bring this up to 2 bits. We're going to go a little bit at a time here. Okay, now you see that there are 4 possible values that the signal's taking on the output. It's trying to track that input. So it should sound a little bit better. Let's do 3. You see it takes 8 values, right? Now what you notice up to now is the noise is correlated with the song. As the quantization gets finer, then you get this property that actually the noise becomes uncorrelated with the song and becomes much more like the equations I gave. So okay, you can hear the noise getting a little better. Now we're going to go all the way up to 8. See how it sounds. What? Yeah, we'll do 5, 6, 7, 8. Okay. Now you'll start to hear. This just sounds like a background hiss. It's going to sound more and more like that, like it's just a hiss that has nothing to do with your music. Okay. And the volume of that hiss is going to decrease, just as we said it would with our equation. It's because the noise power is given by the equation. All right, we'll get up to 8. For me, I could still hear 8, and then it's getting almost to the point of not being able to hear. All right, so here's the last one I'll do. Now, like I said, 16 is the standard for CD audio, and so the original that I played for you is probably about 16 bits, all right? And you really can't hear the noise there. Okay, all right, thanks. Well, I think with 8 you can still hear it. If you're, here I'm just playing in a room like this. If you had like your headphones on, you'd probably still hear 8. But maybe 12 you wouldn't be able to hear.